Hi, I'm Ned, and I make games. In this video, let's draw all kinds of rectangles, all in a shader, using signed distance fields. Things can get pretty complicated, but we'll start with a simple rectangle and add on rotation and rounded corners, before showcasing some more advanced shaders using them. Signed distance fields, often abbreviated as SDFs, calculate the distance from any arbitrary point to a specific shape. Let's craft one for a straight-lined rectangle centered at position 0, 0. To do that, write a function that takes in two arguments, p, the point to calculate the distance from, and the dimensions of the rectangle. So we'll start by finding the distance from p to the rectangle center. This is just the length of p since the center is at the origin. Once subtracting by half the dimensions, we get the distance from p to one corner of the rectangle. The rectangle is symmetric around the origin, 0, 0, so we can expand this to all corners by calculating the absolute value of p. To work this into a solid rectangle shape, rearrange the formula and notice just what the variable d contains. By subtracting the half width, d.x is positive when p.x lies outside the rectangle. This also holds for the vertical axis. Remove negative values, and we have the distance from the edge of the rectangle. However, this isn't a true SDF, which should return negative distances when the test point is inside its shape. To fix this, realize that both components of d are negative when p is inside the rectangle. Find the largest component, which is the one closest to 0, to get the smallest distance from the edge, and then make sure it's negative. Adding this term to the formula gives us the final SDF for an axis-aligned rectangle. But what if we want to recenter the rectangle? Thankfully, it's really easy. Add an offset argument and subtract that from p. This transforms p into a new point, q, which is in the same space as the origin-centered rectangle. Then we can use all the same math that we did before. Let's use this transformation idea to implement rotated rectangles. Add a rotation argument and use it to create a rotation matrix to rotate q. First, take the sine and cosine of the angle, construct the matrix like so, and multiply with q. If you'd like more information about how transformation matrices work, check the video description. Regardless, now q is in the centered, axis-aligned space that our formula expects. Here's an alternate way to define a rotating rectangle SDF using 2 points and a thickness, which may be easier to work with. This one defines the dimensions as the distance between the points and the thickness argument, while the offset is the average between the points. By normalizing the vector pointing from b to a, you can also get the sine and the cosine of the rotation angle, allowing reconstruction of the rotation matrix. How about rounded corners? This isn't actually too difficult to implement. Notice how, as the SDF moves away from the edge, the corners naturally round? We can leverage this by adding a rounding factor to d, subtracting it after the final calculation. This is akin to expanding the SDF, then retracting after measuring the distance. Notice that negative rounding factors make the SDF more pointy all around. A pretty cool effect. It's even possible to apply a different rounding factor to each corner. Change rounding to a float 4 type, and then let each component define the rounding factor for a specific corner. After calculating q, test which graph quadrant it resides in, and choose the appropriate rounding factor. Be careful though, setting extreme values will create some ugly seams. So we finally have the completed rectangle SDFs in HLSL form. You can use these as is in the shader graph by setting up some custom functions, but it's not that difficult to translate these formulas into shader graph nodes. First, create a subgraph for the axis-aligned rectangle SDF. Translate the formula like so, being sure to include rounding. Then create subgraphs for either version of the rotated rectangle. Both can transform p into q and then rely on axis-aligned subgraphs to take care of the rest. Here's the graph for the angle method and the thickness method. Let's make a shader graph which will draw a rectangle along any 2 points. We can then make an accompanying C# script to control it. Set up the SDF by feeding into it the world position and several properties. Be sure to set the properties' reference names for easy use from C#. To transform the SDF into a line, take the absolute value of the SDF, then define a thickness and smoothness property and route everything through a smooth step node. Saturate, then interpolate between the 2 colors. Now, here's a little C# script which sets 2 points based on the mouse position, and another which increases the rectangle's thickness with the scroll wheel. Set up a quick scene and material, and get to drawing. If you'd rather do the same thing with an axis-aligned rectangle, it's much the same process. However, our formula expects dimensions and offset instead of 2 points. It's pretty easy to calculate. Let's make a cool rainbow shader to help us visualize the SDF field. Set up the SDF just like before, then feed it through this graph to segment the field into several colors and animate it. I just love this effect. It's really pretty. It'll work with just about any SDF that you throw at it. Finally, I'd like to demonstrate a more practical use of these SDFs with a procedural brick material. This shader recreates a wall of bricks using rectangle SDFs, noise, and some fancy math. The trick is to segment the space into a brick-sized grid. Then you can offset rows by their row index and create a unique noise seed for each brick, making them feel more haphazardly placed together. And with that, I think that we're done with rectangle SDFs. If you liked this, I have a similar video on a line segment SDF, and I plan to cover more shapes. Is there anyone in particular that you'd like to learn about? Please let me know in the comments. I want to take a moment to thank my patrons for helping make this video possible, and give a big shout out to David Crew, my next-gen patron. Thank you all so much. If you'd like to download the project files from this video and more, consider joining my Patreon too. If not, that's no problem. Either way, you can really help me out with YouTube's algorithm by liking this video. And be sure to subscribe for more weekly game development tutorials. Thank you so much for watching, and make games.